Take note, concept summary, families of exponential functions. Take note of the information here, but it will be broken down in greater detail on the next few slides. First, the parent function, y equals b to the x power. When graphed, looks like this. Here's an example, y equals 2 to the x power. Note the horizontal asymptote at y equals 0 and a y-intercept at 1. When x is 0, y equals 1. And now, while an absolute value of a being greater than 1 leads to a vertical stretch, here we see a compression when 0 is less than the absolute value of a, which is less than 1. In this case, the parent function is y equals 2 to the x power, and the compressed function is y equals 1/2 times 2 to the x power, where for each input x, the output y is compressed vertically by a factor of 1/2. Now, if a is negative, we have a reflection in the x-axis, as seen here, the parent function in orange and its reflection in the x-axis in blue. Translations. A horizontal translation by h and a vertical translation by k. That's when h and k are found in the equation as shown here. Y equals b raised to the x minus h power, horizontal translation, plus k, vertical translation. Problem 3. Using an exponential model. Temperature. The best temperature to brew coffee is between 195 degrees Fahrenheit and 205 degrees Fahrenheit. Coffee is cool enough to drink at 185 degrees Fahrenheit. The table shows temperature readings from a sample cup of coffee. How long does it take for a cup of coffee to be cool enough to drink? Use an exponential model. Now consider the table at the right for time in minutes, 0, 5, 10, and so on through 30 minutes, and temperature in degrees Fahrenheit, beginning at 203, dropping to 177 after 5 minutes, and so on until after 30 minutes we reach a temperature of 104 degrees Fahrenheit. First, consider what you know. You know a set of values in the table, and you know the best serving temperature, 185 degrees Fahrenheit. Then consider what you need. You need the time it takes for a cup of coffee to become cool enough to drink. And so your plan? Use an exponential model to find the time it takes for coffee to reach 185 degrees Fahrenheit. Step 1. Plot the data to determine whether an exponential model is realistic. Here we can see what the data may look like plotted on a graphing calculator. They'd look similar on Desmos. It looks as though we have a decline that's not quite linear. It has a curve and the decline seems to be slowing, so an exponential model may fit these data well. Step 2. The graphing calculator exponential model assumes that the asymptote is y equals 0. Since room temperature is about 68 degrees Fahrenheit, subtract 68 from each temperature value. Calculate the third list, so a new list of y values, by letting L3 equal L2 minus 68. This new scatter plot can be seen here, exactly 68 units closer to the x-axis. Step 3, we'll use the exponential regression L1, L3 function on the transformed data to find an exponential model. Of course, we could use exponential regression notation on Desmos to find the same exponential model. Step 4. Taking the model, the equation given in step 3, we'll translate y equals 134.5 times 0.956 raised to the x power vertically by 68 units to model the original data. Use the model y equals 134.5 times 0.956 raised to the x power plus 68 to find how long it takes the coffee to cool to 185 degrees Fahrenheit. Noting the table, an x value of 3.1 leads to a y value of 184.99, incredibly close to 185 degrees. And so we can state, the coffee takes about 3.1 minutes to cool to 185 degrees Fahrenheit? Your turn, part A. Use the exponential model. How long does it take for the coffee to reach a temperature of 100 degrees? And part B, a reasoning item. In problem 3, would the model of the exponential data be useful if you did not translate the data by 68 units? Explain.